Okay. All right. So today kind of takes us back to something that we looked at last week. And um, in a normal scenario, I probably would have had to set this up in class and then we could have worked through it. But we're going to kind of skip all that, setting up the spreadsheet, just because it takes a really long time. And for this particular problem, this lady saves for 75 years. So I don't want to make 75 different lines on. Uh, Dave, I'm gonna mute you because I think there's a little bit of feedback. Okay.
All right.
Okay. Okay. Yeah. So I don't want to make like 75 lines on these on what do you call it, on this spreadsheet. So we're just gonna kind of skip a couple parts here. We're gonna try to work on the part where um, we're gonna try to see if it results in 100. So we're going to basically skip part A, right, where it says to study the beginning of the spreadsheet, discuss with the partner what each cell and formula represents. We kind of did that last time, right? So each cell just kind of represents how much her balance is growing by every year, depending on the interest rate, and then the additional yearly savings that she keeps adding into it. Okay, so the spreadsheet helps keep track year after year. So if you really did want to kind of like see what's going on, you could type in what you see there on a new spreadsheet. Okay, so right then part B then says extend the sheet to cover 75 years. Does this choice of beginning balance, yearly savings, and interest rate result in 150,000 saved after 75 years? Okay, so without doing the spreadsheet, there's another way that we've been looking at in order to be able to determine whether we can reach a certain goal, right? And so that formula that we've been using has been, right, going back to number 4 where we first saw it, right? It was the recurring value formula, or the future value formula with the recurring deposit. Okay, so we can estimate whether this lady, or what her final balance will be, okay, after 75 years based on the conditions, right? So we just have to utilize this formula just to kind of double check and do a quick analysis. All right, so that's kind of where we'll start. So here for part B, so we know all along that this represents F equal 1, I'm sorry, A times 1 plus the rate to the power of T plus A representing your recurring deposit, followed by 1 plus the rate to the power of T minus 1 all over the rate, right? So basically here, the scenario was, going back to the original. So the following portion of a spreadsheet can be used to explore how Miss McCarthy, this is like the really old woman. We saw this back when we were still meeting in person. It's trying to show us how she could have saved 150,000 in 75 years. And so would the current settings, right, her having an initial balance of $25, depositing $100 a year at an interest rate of 5%, will that get her to $150,000 saved in 75 years, right? So that's the question that we're trying to answer. And so what we can do here is just fill in what we know, right? We know that the initial deposit in this case would be $25. Okay, 1 plus the rate. The rate is already set up for us here as a decimal. So we can go ahead and just use that. And so when we add 1, it'll be 1.05. And then the time that we're trying to determine whether this will happen in is 75 years. So it's just 75 to that power, okay? Plus, now the recurring deposit is the $100 that she's gonna put in annually. And then now the rest, we can utilize 1.05 to the power of 75 minus 1 all over 0.05, okay? So then this will kind of tell us whether she will be able to reach the goal right, by depositing 100 and having started with 25. I don't know, it seems like she might fall short, but let's find out. So in this case, let's calculate. Let's start off here with let's start off here with the first part. So we have 1.05 to the 75th power, okay? And then that value, we'll leave it like that, don't round it. We multiply that by 25. And so here we're looking at $970 with 82 or 80, yeah, 82 cents. So 970. Okay, plus now let's do the second half. So once again, starting here in the numerator inside of those parentheses, 1.05 to the 75th power. Subtract 1 from that. Divide this by 0.05. All right, and then multiply this by 100. Okay, so we're looking at here 75,665 with 37 cents. Okay, so clearly she's gonna fall short, right? You have 75,000 plus another $900. She's not even, she's about halfway to 150,000. Okay, so let's just add it up real quick. We get a final total. Okay, and so we're looking at 76,636 with 19 cents. Okay, yeah. All right, so what becomes kind of the interesting part about the rest of the problem is clearly her starting with $25 in the account and only depositing $100 a year is not going to get her to her goal, right? Basically, it's really almost like she only saved about $1,000 a year, right? $76,000 after 75 years, right? It's not enough. So part C basically has us look at experimenting with changes in the entries for initial deposit, the yearly savings, and the interest rate, right? And we want to come up with different combinations so that we can get to 150,000 in 75 years, okay? So this is the part right now where you guys can go ahead and unmute yourselves and let me know, like, what do you think one factor should be changed between the bank balance or the starting bank balance, the yearly savings, or the interest rate? What do you think could be changed there to help her get to her goal within the 25 years? What do you think would be a good choice? I think.
Would it be the amount that she deposits each time?
Yeah. So, okay. So maybe instead of 100, what do you think might be a better choice?
Um,
You don't have to calculate it out right now. Just kind of throw a guess out. Like, what do you think you would need to deposit every year to get to 150,000 after 75 years?
mm, wouldn't we have to? I don't know. I just woke up.
All right. Well, how about we try maybe like 250? Right. What if instead on a yearly basis she's depositing 250? Right. We're going to keep the bank balance the same, right? Starting at 25 with the interest rate at 5%. And let's see if then that changes, right? So now we have like a different setup. And let's see if this will work. Okay. So the first part of the formula, notice how the first part of the formula doesn't generate much for her, right? The initial amount that which she starts with, it doesn't really seem to have too much of an impact, right? Because after those 75 years, it really only earned her the $970. But the reason why I was asking what should her yearly deposit be, because this is where you seem to be getting a much larger return, right? It's that initial constant deposit that is adding some interest onto it year by year that is getting her results, right? Not so much what she started with. So that's why I'm saying like we'll leave the 25 for now, but we're going to increase from 100 to 250 and see if that makes a difference for her. Okay, so the first half is still going to be the same. That's 25 times 1.05 to the 75th power. We already know that that's going to generate the same amount of money for her. Okay, but this time we're going to change this to 250, right? Which is still pretty doable, right? To save $250 a year, right? It's not even a month, it's a year. So 1.05 to the 75th power minus 1 all over 0.05. Okay, all right, so now let's calculate and let's see what we got. Okay, so 1.05 75th power minus 1 divided by 0.05. Okay, and then we multiply this by 250. All right, so this will then generate 189,163 with 43 cents, right? Okay, so clearly that reaches the goal, right? Like way past the goal there. She went much higher than what she really initially wanted to. But if we just add everything up, we'll kind of arrive at this final total. 63. Okay, so if she were to deposit $250 a year instead of just 100, she can actually reach up to $190,000, $190,000, 134 cents. I'm sorry, $134.25. Right? So what might not seem like much, right? After the course of 75 years, right? It's quite a lot, right? $100 barely gave her about 1,000 a year versus 250, right? This is where she's at. Okay, so now that you kind of have an idea of how that works, right? It's a relationship between the three things, right? The APR, what you start with, and the yearly savings. The two biggest factors really are dependent on the rate and the yearly savings. Those are the two biggest ones. Typically, what you initially put in is a very small fraction of what the overall savings will give you, right? And you can see the comparison here, right? So let's say you decide one day, like I have like $10,000 and I'm going to put that into my savings account. But then after that, I'm only going to save about $100 a year, right? It's like, okay, you started with a really big amount and that's great, but then you didn't really keep up with it at the pace that you could have, which could have resulted in much higher returns after, a lifetime of working. Okay. And so, these are kind of, if we were in class, I would have given some time and would have said like, okay, find some different options. We would have tested them and then we would have seen like who could have given us, something that works. So a couple of different ones that were given here, because this is only one combination, right? Where we have a $25 starting, 250 recurring, and a 0.05%, I'm sorry, 0.05 rate. So it's a 5% rate. Some of the other options could have been initial, could have been 100, right? So she starts with $100. Her yearly savings is 200. So this is her recurring. And then we keep the interest rate at 5%, right? That's option A. Okay, that would have worked. Another option also could have been that we keep the balance the same, kind of like what we did, right? We kept the initial the same. They adjusted the yearly, right? They actually bumped it. Well, they kept it at 100, but then what they changed instead was the rate, right? The larger the rate, you're going to continue to see some returns, and I believe they left this at 6.3%. Okay, so this is what I mean about you can change any of them, and you might reach the goal that you're looking for, right? In this case, it was just about increasing the rate. right? And even though it doesn't seem like much in comparison to a 5% to 6.3%, you got to think that this is compounding, right? And with compound interest, you're adding a little bit more to it the next year, and then you take 6% of that, and then a little bit more, and then 6% of that, and so it's growing much faster. Okay. And then a couple more options. They gave us option C and option D. If initial you started with 200, and then on a recurring basis, you just increased it by $10, right? And if you would have kept the rate at 6% this time, right, you would have reached the goal. And then the last option was an initial of 250 with a recurring of 140 and an interest rate of 5.5, right? So a slight increase in the rate, a larger initial, and then a $40 increase in your recurring. Okay, so these are just examples. Okay, these are examples. This doesn't mean that these are the only right ones, because clearly we found one, right? We found one that worked. Okay. All right. So that's pretty much it. Let's see. Yeah, the rest is just like discussion questions. Okay. Are there any questions on what we just kind of looked at here? Doing okay so far?
Yeah.
Good. Okay. All right. So now for the next one, we're gonna skip number 7. We're gonna jump into number 8. Number 7 again was one of those types of questions where we would have like spent some time in class. We would have done it where we estimate what kind of scenario do we need to get to $1 million, right? So you would have come up with an initial, recurring, and then a rate, right? Something that could then get you up to $1 million within about 60 years. Okay, so we're gonna go ahead. We're just gonna kind of skip over that. We're gonna jump into number 8, and so there is a tool that we're gonna use. Let me show you where to find it. I'm gonna go to Schoology, and I'm gonna show you where that tool is at. So I uploaded it into the course materials for the week before spring break because I thought we were gonna get to number 8, but we didn't. So let me show you where to find it. Okay, so right here, do you see inside of the yellow folder, online week 3? If you click down, you're gonna see this black folder that says materials. Okay, so if you click on it, there was two different links. One of them is a spreadsheet. So we did that before. Don't worry about going there. I want you to click on the one that says compound interest simulator. And if you click on it, it should take you to this like this graph, interactive graph. And then you might have to click and enable your Adobe Flash. So for some of you, if you click on it, you just have to hit allow if you're on a Chrome browser. Okay, so you should see something like this. Okay, so go ahead and try to get there, and then we'll go back to the question, and then just let me know if just put it on the chat if you were able to open it up. All right, were you guys able to get there?
Yeah.
Yeah? Okay. Anybody else? If you're having a hard time, it's okay. I'll go ahead and just show you right here on my screen, kind of basically how it works. Okay, so let me switch back to the other. Let me just share my whole screen. Okay, so basically what we're looking at here is this is an interest simulator where it basically gives you an idea, or not an idea, but it actually calculates for you what you can expect to be in your account based on how much you initially deposit and how much you contribute and the interest rate that you, let's say you open an account and there's an interest rate there. You can determine, you can kind of map out to see like, okay, what is it going to look like 10 years, 15 years from now. All right, so for the question that we were being asked to find here is right, this is a helpful tool for what if questions. And so just to kind of give you some background, I've had a lot of time this past month. So I opened up an IRA account. It's called an individual retirement account. So when you open up these accounts, basically what you're doing with your money is you're finding a place to invest it in, somewhere in like the stock market or in treasury bonds. Basically, it's like the stock market, but you're using that money and there's certain limitations because you're holding it out for retirement. So you're really not planning on touching it for at least in my case, maybe at least like 35 years or so. My what if question is like, well, how much should I put into it now and how much should I contribute it monthly so that I reach a certain number so that when I reach retirement, I have enough to kind of live off of. And so let's just say that number is like 1 million, right? I've heard, I don't know exactly, but I've heard that like that's kind of like the rough estimate. Like when you retire, you want to have $1 million because let's say you retire at 65, average life is like 80, right? So you still have like another 15 years to live after you retire. So you want to make sure you have enough money to cover your expenses, right? But when you retire, you might not have a house payment anymore, right? Hopefully you already paid off your house. You might not have a car payment or a brand new car payment. So really it's just like money to travel or money to eat, your groceries. So like simple expenses that older people don't have that younger people might, okay? So the what if questions are important, and so it's nice to have a tool like this to be able to go back to and say like, okay, this is going to help me plan out. I need to then put some money aside for savings every month to reach that goal. All right, so the what if question is, suppose you decide to open a savings account with an initial deposit of 100, right? So our I value is 100. The account pays an annual interest rate of 2.4% compounded monthly. Okay, you plan to make regular monthly payments of $50 into the account. Okay, so 2.4% monthly, $50 every month. Okay, so let's go back and let's see if we can utilize this. All right, so in this case, we don't really have the option of choosing monthly. So hopefully, or actually, yeah, because it's a monthly contribution. Okay, so it is in terms of a monthly. The principal is 100. The monthly contribution for us would be 50. Okay, and then we have to change this interest rate because we're not going to be able to get that, right? So it's actually at 2.4%. Okay, so that's our scenario, right? So what we see down here is these two different graphs. One is green, one is blue. And so I want you to, right here in this yellow box, it kind of tells you the breakdown. Okay, so the time that's elapsed is 10 years, and that's basically what we're being asked to find because part A of the question tells us to look for. Sorry, I'm trying to show it. Yeah. So it says, according to the computer display above, what is your balance in the account after 10 years? Okay, so let's kind of go back to it. And here it's telling us that the total value, right, in your account is going to be $6,900.71. Okay. Now, the reason why you have a blue and a green is to differentiate between how much money you contributed versus how much money was earned in interest over that period of time, right? Remember that the total value is composed of both factors, how much money you put in as well as what the interest rate is earning for you. Okay, so you can tell right here that the principal contributions, the principal plus the contributions, that represents your principal initial amount, right? What you put into the account when you first opened it. And then all of the contributions represent the $50 every month for the next 10 years, right? So just if you do the math real quick, 50 a month for a year, so that's 50 times 12, that would give you $600, right? $600 a year times 10 years, that's the 6,000, right? So you have your 6,000 plus the 100 you initially put in. That's why your principal plus your contributions is 6,100 exactly. Okay. But in that period of time, notice how the interest rate was working in your advantage, right? 2.4% of your monthly contributions was, right, adding on to your account. So then interest to date, meaning that up until those 10 years, now you have $871 of interest earned. So then when you add it all together, then that shows you your blue line, right? So you have your green is growing at what we call a linear rate. It's constant, right? It's only increasing by those $50 a month, right? So it's a very linear graph. The blue one does not grow linearly, right? This is the benefit of compound interest, is that compound interest grows exponentially, right? So you have a faster growth in your blue than you do in the green. The thing that makes that go is the interest rate, right? So just kind of bear with me here. If I change this to 50 years, you're going to see the exponential curve a little bit better, right? So now look at the green, right? The green is still your contributions. It's still just flat, right? Growing at a constant rate. But then the blue, you can see how that has become a much clearer exponential curve because we've expanded the time, right? So obviously the longer you go in terms of time, the larger your interest rate gains will be, right? So look, you've contributed after 50 years, right? Let's just say you open an account right now. You guys are what, 18? Okay, so if you probably, yeah, if you chose to retire 15 years from now, you guys would be about 68. Yeah, so let's just say that this is your scenario, right? You start opening an account with $100, and then you decide I'm going to save $50 every month, put it into that account, and I have an interest rate of 2.4. By the time that you reach those 50 years, by the time you're 68, you contributed 30,100, right? Pretty good. But look at the interest that you've earned over that time, 28,000. It's almost as much as what you contributed, right? So that's a pretty good deal in terms of being smart about where you put your money, because it's basically doubling what you contributed yourself, right? Without having to do much besides just put it away into an account and then just, not touch it. All right. So this is kind of like a nice little way in which we can keep track of all of this. Okay. So let's go back to the 10 years and let's just answer some of these questions below. Okay. So according to the computer display, what was the balance in the account after the 10 years? Well, the balance was 6,971. I'm sorry, before I go there, are there any questions about the tool or how to read the graph? We're good?
No, we're good.
So far? Okay. All right. Cool. Okay, so then let's answer the question here. So 6,900 with 71 cents. Let me make that clear. Okay. How much interest did your account earn after 10 years? Okay, so then that would be the interest to date. So that's the $800 with 71 cents. All right. And then examine the graph displayed on the previous page, okay? What part of the graph represents the total value with interest of your account as a function of time? What clues did you use? Okay, so that represents, what part of the graph represents the total value, right? So we already discussed that the total value is represented by the blue, right? Clearly it says total value, right? So that's the clue, right? It tells us. So the blue function, okay, that's our total value. All right. And then what part of the graph represents only the money you contributed and no interest as a function of time, right? Well, we talked about that as well. That would be represented by the green function. Okay, why does the pattern of change shown in the graph make sense? Well, we talked about that too, right? The green function is a linear growth. You're only depositing a certain amount each month, right? So it's only going to grow by 50, or it's only going to grow by 100, or it's only going to grow by what you put into it. Unless you decide willingly to say, okay, first month I'm depositing 100, then the next month 150, then 200, and then it would change. But let's just say you're consistent the entire time. The green function is represented with a linear growth. Okay, the linear growth represents your contributions, right? That's essentially saying how much you contribute to your own account. Okay, and then the last part, it's asking how is the interest earned represented on the graph? What could we say in regards to that question? Where is the interest that you're earning? Where does that show up? What are your thoughts? Right, so do you see how there's a little bit of a separation, right? As time goes on, you start to see this little gap in between the blue line and the green line. Essentially what we could say is that the interest is represented by, if I were to slide this, I think I could slide this actually, no? Oh, okay. So if I slide this along, right, you see that gray bar moving, there's a gap in between red and, I'm sorry, blue and green. And so that gap, that difference is your interest, right? That's how it shows up. It's the space in between those two graphs, the difference between them, right? So we can say that it's the difference between the total value and the contributions. Okay, but otherwise it's pretty easy to read. Okay. All right. So now for part D, it's asking us to access the above financial calculator to help answer the following questions. Okay, so how many months before your account balance will be at least 6,000? And then how many months before your account balance will be at least 10,000? All right, so let's go back and see if we can figure this out. So we want to know when it's going to be at least 6,000. And by that we mean the total value, right? So we don't want just our contribution to be 6,000. We want the whole thing. So right around here, okay, we reached the total value of $6,020, right? So just above the 6,000. At this point in time, if you look down here on the x-axis, you have your years marked. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So about after 9 years, we're reaching, or actually, it even tells us right here, time elapsed 8 years and 10 months. So not even the 9 years. It's a little bit before that. So let's go back. After how many months? Well, because we're talking about if they give us an answer here of 8 years and 10 months, but they want the final answer in months. Just make this conversion here, right? The 8 years, multiply that by 12, you're gonna get 96, okay? So 96 plus the 10, that's gonna be after 106 months. Okay, you're gonna have at least 6,000 at that point. Okay. And then for part B, so this is for 6,000. Right, it's gonna take about 106 months. And then for the 10,000, let's go back and we might need to expand this. So we might want to push this out to 30 years. And we'll go backwards. Oh, too far. Okay, so right here, right between 13 years and 10 months and 13 years and 11 months, it makes the jump from just under 10,000 to just above 10,000. Okay, so for us, the total value would be, okay, so for 10,000, $13 years plus 11 months. Okay, so let's just make this conversion back to months. So 13 times 12, 156, I think, plus 11. So 167. Okay, so 167 months to have at least 10,000 and 106 months for at least 6,000. Okay. And then the last one is just, what is your best estimate for when you will have earned 1,000 in interest? Okay, so that right there is a different question, right? Not when you're going to reach 1,000 is the total value, and not when you're going to contribute 1,000, but around when will you have earned $1,000 in interest, right? When will you see a gap between the two lines that represents $1,000? Okay, so we can use the same tool, right? But this time you're looking for here interest to date, right? You want to be able to identify when have I reached 1,000 by looking right here. All right, so let's keep going back. So right here we're at 990, and then the next month, then that jumps to just over 1,000. Okay, so that tells us 11 years and 2 months. So for part 2, $1,000 in interest will take 11 years and 2 months. Okay, so the 11 years multiplied by 12, so we can turn it into months. That's going to be 132 plus 2, so we have a total of 134 months. Okay, to earn $1,000 in interest. Okay, and so that's pretty much it for that one. All right. Do we have any questions so far about the tool, the calculator, any of these problems?
No.
We're good.
Yeah.
Okay, all right, and so then we'll just finish up with number 9. I just wanted to review something real quick. All right, so we kind of have an idea of how this works. So if you ever are curious about how much money you can make over a period of time, you want to be a millionaire one day, let's say you start off with about 500 bucks, and every month you deposit, say 300. And let's say you have a little bit of a better interest rate. Typically, the average interest rate in like a retirement account is like 8%. So let's just go with 8.5% or so. And let's say that you have been saving for about 30 years. Okay, maybe it's not 1,000,000, but it's about 500,000, so maybe about 500,000. Okay, so those are the kinds of things that you want to think about. Um, maybe just like right after you get out of college, you start thinking about, okay, like now that I have a little bit more money that I'm making, what do I do with it? What's a smart way to kind of set myself up for the future? This is a good way. You invest not just by saving it into an account where you don't really get anything back, which is what the big banks do. We've talked about this. The other day, I got another penny deposited into Wells Fargo. That was cool. Um, so that's how little they pay in terms of interest. So you want to find a different type of account that kind of generates a little bit more for you. And so this is something that, hey, like, you just keep moving on with daily life, and next thing you know, you have a nice something to set you up for a couple of years. Or a lot of people, they sometimes take money out of their retirement accounts and they buy a house because there's exceptions in certain accounts that allow you to do that. So you just have to do research. I'm sure you guys have heard of like 401k, or maybe your parents have a 401k or a Roth IRA or a 403b. They're all a little bit different, but sometimes they allow you to withdraw your money even when you aren't retired to buy a house. So there's just different.
Mister, what if I don't live for 30 years?
What if you don't live for 30 years? Then you assign a contributor, or I'm sorry, not you assign somebody to receive that money for you. So you could leave it to your kids. You could leave it to, if you're married, you leave it to your spouse. You could leave it to your parents or a sibling. Yeah, so that the money doesn't just get lost. At least you leave it to somebody, and I'm sure you'll live for 30 years. Goddamn, don't worry.
What if I don't leave it for no one?
If you don't leave it for anybody, that's a
Yeah.
good question. I think it can be seized by the government.
Oh,
At the worst case, just donate it. Like, find a charity, donate it to like a kid's hospital or something. Yeah. Yeah. All right. Okay. So last thing, we'll just wrap up with number 9. There's something that's kind of important about that one. We'll talk about it. Okay. So here's our friendly neighborhood formula. We've been using it a whole bunch. All right. So the future value of an investment. There it is. Right. We've been using it. Okay. Recall what the variables I, A, R, and T are. We know what they are. No need to do that. Now, here's the important part. It asks, how would you modify this formula to calculate the future value of an investment paying APR? And then here's the key. What if it was compounded monthly? Okay, because so far, I don't know if you've noticed, but so far, every time we've used the formula, the type of interest was annually, or it was compounded annually. Right? If you go back to all of the problems we've done, you'll see a key word there where it was like the annual percentage yield, right? It was annual, annual interest, compounded annually, right? So at no point did we ever have to consider like, well, what if now we have to compound this on a monthly basis, right? So we can still use the same formula, but we have to adapt it. We have to change it. Kind of similarly to how the compound interest formula goes. Okay, so we're gonna take a trip back in time. And we're gonna take a look at how is compound formula set up in a way to allow for compounding besides annually, right? So take a look here. The original compound interest formula, which we stopped using a while ago because it didn't give us the ability to find out what we would get with these recurring deposits, it had this right here for us, right? Where it would take the rate and it would break it up. It would divide it, right? So on the numerator, I have R, and my denominator, I have N. N represented the compound, right? How many times we would compound it. And we're basically looking to be able to utilize it when we do things monthly rather than annually. So if my N is utilized in this compound interest formula, right? Not only once, but twice up here, because we're breaking it up several times a year, then how do we then make it fit over here so that it's also possible, right? Notice that whenever we had R, we would have to divide by N, and anytime you had a power of T, you would have to multiply by N, right? So think about what would need to be changed to this formula now to allow us to have the flexibility to use compounded monthly semi-annually. Like, what do you think needs to change about this formula? Any ideas? Anybody have a guess?
What was the question? Because the audio kind of messed up.
Oh, the audio is not good? Okay. So the compound interest formula has a built-in method to allow us to compound things besides just once a year, right? We can do them weekly, monthly, because the n, there is a space there for us to put. We could put in 1, we could put 2, we could put 12, we could put 52, right? Depending on how many times we're going to compound something in a year. But the recurring formula here, the future value with the recurring deposit, this formula here that we've been using doesn't have the capacity for that because it doesn't have n anywhere, right? So this is assuming that it can only be done annually. But what if we change the formula up just a little bit? What if we changed it to then make it flexible so that we can utilize it with a new variable n? Right? What do you think we could do here with R, with T, with this R, with this T, with this R?
Shouldn't you divide it by the time period?
The time period or the compound period?
The compound period.
Yes. Okay, good. So whenever we have R, we're going to have to divide it by n. Okay, so I'm going to put everything that's new in green. Okay. So we can divide the rate by n, and then wherever we see R, we'd have to do that. So then down here, we would divide this by n. We would divide this R that's inside of that parenthesis. Let me erase it. Change this to R divided by n. Okay, so that's one thing. But where else is n going to be necessary?
With the time?
Yeah, with the time, right? So basically, it's exactly how the compound interest formula is set up. We do the same thing with the future value formula for the recurring deposit. The rate is always divided by the compound period, and then the time is multiplied times the compound period. Okay? So it does make the formula a lot more messy, but it does then allow us to find out what is that future value going to be if I'm compounding things monthly versus only once a year. Okay, so we were limited before, but now we're not. All right, so now let's go back to number 9, and then I'll draft it up over here. Where'd it go? Okay, so if we wanted a formula that allows us to compound things monthly, okay, or any in general, okay, what we want to do is keep some of the parts, right? F is equal to our initial times 1 plus, but now I have a rate that if I do things, let's say monthly, that rate is going to get divided by 12, right? So that I know the specific interest rate just for that month. Okay, so then I can utilize n down here in the denominator. Then we would multiply it times, or take it to the power of t, right? But because this is now monthly, or maybe semi-annually, or quarterly, right? I need to know how many times that's going to happen in a year, or in that, let's say, 5-year period. So then I can't just use t, I have to use t times n as well. Right? So those are the changes that are necessary for that part of the problem. Okay, then plus a stays the same. In the numerator, we have 1 plus the rate. And again, because I have rate, I need to divide that by n. I have a power of t, which is time. So if I have time, I then need to multiply that time times the number of how many times I'm going to compound it in that amount of years. minus 1. And then my denominator is another fraction because originally I had just r, but now r needs to be divided by the number of times that it's going to be compounded. Okay. Are you guys with me so far on that?
Yeah.
Yeah.
Yeah, so it's just blending the two formulas that we know, just blending them together. And so now we have all of the different possibilities. Now we have something there for it. Okay. All right, so then real quick, it's just asking us to compare the formula. Oh, no, we're not gonna do that. Agree, determine the future value. Just gonna compare the future value calculated by formula with the total value of the previous plan. Okay. And then compare the amount. With the situation to the amount displayed in the elements. Okay, all right, we're not gonna do that because all of the answers are gonna be pretty much like they're the same. Okay, but now we have this new formula which is like can be used in any situation. So let me just kind of give you an example, right? Let's say we wanted to find out what would the final value be if we had an initial amount of, let's say, 400, a recurring deposit of 250. We had an interest rate at 3%, but it's compounded, let's say, quarterly. Right? And because things are quarterly, that means 4 times in a year. Okay, now we have the option to be able to find that final value, because before we introduced n into the formula, we were assuming that the only way it could have been done was annually. Right? Because imagine that the denominator is 1. Here, this is a 1. That's a 1. There's a 1 there. There's a 1 there. Right? When you divide by 1, nothing changes. But when you divide by something else, obviously you are going to have a change. So what we're saying now is that this formula now allows us to compound things, not just annually, but it could be anything else: monthly, semi-annually, quarterly, weekly, daily, and we can find the final value. Okay. All right, guys. So I think I'm gonna leave it there. Yeah, we're gonna leave it there for now. The only thing I'm gonna ask you guys to work on is go ahead and just try the CYU on your own, so that we can check in on Tuesday and we'll go over it together just to see how we're doing. It was a really long lesson, right? It took like 4 or 5 different parts over the course of like 2 weeks. So I just want to make sure that you're still able to do some of this on your own, okay? So just try your best, work it out whenever you get a chance. The CYU is on page 282. Okay. And I think it might actually ask you, you can actually use the tool, I believe, the tool that's in on the Schoology folder, okay?